All right, we're back. We're still on page 12 of note 17, I think. Yep, of Calc C. And what we're doing is finding polar areas. And this question is going to be all about rose curves. Our ability to answer this is really going to depend on our ability to understand how to graph a rose curve in rectangular, right? So how does the rectangular graph become the polar graph? If you can answer that, you can definitely answer this without creating the polar graph. So I do not want to create the polar graph. What I want to do is create the rectangular graph. And then I don't even need that much of it. I just need enough to know what's one petal of this thing going to look like, right? So the period is 2 pi over 3. So the increment is 2 pi over 3 over 4, so 2 pi over 12, so pi over 6. So what's going to happen is go to pi over 6. I'm going to start at a maximum. I'm going to go here. Now, that is 1/2 of one petal. So if I know how many petals I need, I can use this information and just multiply it up, right? So what I'm going to do is say, there are definitely 3 petals because this is an odd number and you get that number of petals. If it's even, you get twice that number. So 6 petals. Nope, 3 petals, but I'm going to find half. So I need to double that. And then I need to multiply by 3. So I need to multiply by 6 overall. So what are we doing? We're doing 3 petals times, I'm finding half a petal, so I'll double it. And then a polar area, so 0 to pi over 6 of 5 cosine of 3 theta squared d theta. I'm not gonna even mess around with this by hand. I'm gonna let the calculator do it. Alternatively, what if we rewind here, right? And go back to negative pi over 6. This is one full petal now. So I could just do 3 1/2 negative pi over 6 to pi over 6. And then I'll just say r squared d theta. Both of these are going to work. You can get them on the calculator, but it's really kind of not the point to get them on the calculator, although we can. Here, what are we looking at? We're looking at 8 petals. So I need to know that so I can figure out, like, what am I doing? And the period is going to be 2 pi divided by 4, so pi over 2. And then the increment is going to be that divided by 4, so pi over 8. Yeah. I was like, why did I divide 2 pi by 4? But the value, there are too many 4s in this problem. Pi over 8. So I'm going to create the rectangular graph, or part of the rectangular graph. So we're going pi over 8. Really, the pi over 8 is the key thing. If I know that, right, so there, that's half a petal. So I could find the area of half a petal and double that to get 1 petal, and then multiply by 8. So multiply by 16 overall. I could do 8 petals. I'm finding half a petal, so I need to double it to get 1. And then a polar integral 0 to pi over 8. And then let's just say r squared d theta. That'll work. But what if I keep going? This will be 2 pi over 8, which is pi over 6, pi over 8, pi over 8, 2 pi over, oh, 2 pi over 8 is pi over 4. I was going to say it's pi over 16. So that was me not why am I so slow? Hello. I'm back. Okay. So that was me. That little slowdown there was me not understanding that 2 times pi over 8 was pi over 4 instead of pi over 16. I was like thinking that it was. All right. So here I would do 8 petals. My polar area is 0 to pi over 4 of r squared d theta. And that's going to work. Both of those are going to work. So this is the concept. You don't need to create the graph. You don't need the polar graph to find it, as long as you understand where the polar graph comes from. And it comes from the rectangular graph. So this will be 16 petals. So the period is 2 pi over 8, which is pi over 4. I just worked that out. The increment is pi over 4 over 4, so pi over 16. So if I graph a little bit of the rectangular, start here, go to pi over 16, that's half a petal, right? So there's 16 petals. I'm only finding half, so I'll have to double it. And then my polar integral gives me the area. So that's one option. A second option would be to rewind to get here. This will give me a full petal, and there are 16 of them. Wow, man. 16 negative pi over 16 to pi over 16 of r squared d theta. So I like doing problems like this. You get to think a little bit. It's not like the most mentally taxing thing in the world. It's helpful though. So period 2 pi over 50, so pi over 25. So then the increment is going to be pi over 25 over 4, so pi over 100. So now, if I were to start graphing the rectangular, this is going to happen at pi over 100. So that's half a petal. So how many petals are there? There's 100 petals. That's a lot. So we get, is there like a pattern here? Should there be a pattern that I like have messed up somehow? Pi over that is pi over 4, pi over 16. This is pi, 2 pi over 50 is pi over 25 over 4 is pi over 100. 100 petals, pi over 100. 16 petals, pi over 16. 3 petals, doesn't work, but you don't double that one. 4 petals to pi over 4. I feel like there's definitely a pattern that, you know, exists that I bet every year I find, and every year I'm like, that's so cool, and then every year I forget. All right, let's do 100, but it's only half, so I have to double it. 1/2, 0 to pi over 100, and r squared d theta. And then by not evaluating these, I'm also probably losing out on some like amazing thing that happens. What if we rewind? Negative pi over 100. So we can go 100, because there's 100 petals. We're only finding one. 100 petals, and then our polar integral. Pi over 100 r squared d theta. That'll work. These are all going to work. I'm just saying that confidently. Find the area in the third quadrant between the polar curve, whatever that thing is, and this. Okay, so we're going to have to find where they intersect. I'm going to convert this to polar. So this is r sine. I'm going to add this 2/3 r cosine, right? X is r cosine. So I just added 2/3 x to both sides equals -4. So r is -4 over cosine theta plus 2/3 cosine theta. All right, so just now what I'm going to do is I'm going to graph it on my calculator just to like see. Like I have no idea what's going on here. I mean, maybe I have some idea. I have no idea. So let's share a calculator. Yep. Share a calculator screen. And let's change to a graph page, doc4, then graph. Change this to polar, so menu 3, option 5 is polar. What's in R1? Oh, we already graphed this. I already graphed that? Or I just, I stored it as R1, I think. I don't know, doesn't matter. 2t, so notice use t for polar graphs, which is super convenient because theta is like buried in the pi key, bizarrely. T, oh, you have to use theta, great. Why is it t? I guess I define that. Wait, can I change this? No, I cannot change that. Okay, we got to use theta, and it's buried in the pi key, so all of my griping still valid. More valid than when I was griping about it. I got to change all my t's into thetas now. Okay. You got to do what it tells you to do. The problem is it wasn't telling me because somehow I managed to change the theta into a t. And that's alarming. It's because I defined R1 as a function of t, but like I feel like the calculator should be smart enough not to do that. Oh, what do you mean? All right, hold on. Doc4, let's insert a problem. Graph, menu, option 3, option 5. Probably should have done this in a separate video. I can actually type theta, so I'm going to do that. Plus 3 sine of 2 times theta. There we go. Okay. Oh yeah, I always think this looks like a sleeping baby somehow. I don't know. Your thoughts may differ. And then I'm going to graph this, -4 sine of theta plus 2/3 cosine of theta. Oh, okay. I was like super confused, like what region am I looking for? So the region that I'm looking for is this region, right? The region bounded by both of them in the third quadrant. So we're gonna have to zoom in a little bit here. Like, is there something weird going on? And then definitely we just go to 3 pi over 2, right? So I think they're both there when it's when theta is 3 pi over 2. Let's trace 3 pi over 2. So definitely there, definitely there. Okay, so 3 pi over 2 is good. What's happening at the top here? I'm just not sure. I'm not sure if I can just go from, I'm hoping I'm gonna box. I'm gonna forget how to do everything. Zoom box. I just wanna see like what's the story here. Okay, so we can just, I think we can just go from pi to 3 pi over 2. Beautiful. All right, so I'm gonna go from pi to 3 pi over 2. Let's get like a standard window here, something. And then zoom, okay. We're gonna go from pi to 3 pi over 2 of this curve squared minus this curve squared. So the real polary one squared minus the slightly less polary one squared. So let's add a calculator page, and we're gonna do 1/2, because it's polar, integral from pi to 3 pi over 2 of, so the first one I graphed was the little baby one, so that's r1 of t squared minus, the second one is the linear one. You know what's going to happen is if I get a positive, I got them in the right order. If I get a negative, I got them in the opposite order. And then dt. So 64.190, I guess. I hate that. I'm going to handwrite that in here while I'm on it. So pi to 3 pi over 2. And then we did what I wish I had named it, but I didn't. So I'm just like, I'm writing right now. The baby curve squared minus the weird linear one, but in polar. I'll go back to the notes and show you this. I just got to get it all down first. Squared d theta. That is approximately 64.190. Gross. All right, let's go back and take a look. So that was a good problem. Mostly it's like what's the relationship between these curves? And we had to convert one of them into polar. Like that's kind of a big deal. So there you go. Converted it. Graph, the calculator was indispensable there. I don't know how we would evaluate this without a calculator. But anyway, I'm going to end this one here. I'll be back in the next video to do some more. So I will see you there.